and we have then pulley, and we have the 4 kg here. So when we look at the free body diagram, which forces do we have? The most obvious ones first. When we look at the masses, what do we have in respect to that then?
The 4 kg one is being acted by gravity.
Okay, yep. So we can either go by 9.81 or what did you usually do use in the test? 9.8 or 10?
9.81.
9.81, huh? Okay. So we make that 4 times 9.81, and that will result in something. Okay, what about the 10 kilogram mass?
It's being pulled by the weight of the 4 kg.
Right. So, I mean, in any case, what you have in any case is nevertheless the weight force as well. It may not play a role, but it's there. Huh? So just for the completion of the situation, that's obviously 89.1 Newton. This was 39.24. Huh? Is that correct? 24 Newton, I think. Huh? Okay, so these are the vertical forces, but obviously because of the pulley, something else happens, right? So it says that a frictional force acts on the box. So where do I have to put down that frictional force, and in which direction?
On the 10 kg box to the left.
Okay. So we call that R for resistance, for example, huh? And that's 12 Newton. Okay, so what is missing now in that diagram?
The reaction force.
You mean for the normal to the surface?
Yeah.
Yeah, okay, yeah, that is something. We can say that. The normal to the surface, of course, is there as well, but that's just the same as the weight force, okay? Does it matter here? Not really, right? I mean, you may say the normal results in the friction force is related to the friction force. That's what happens, right? But that's not what we are interested in right now. So, because the statement is when the box is released, the frictional force acts on it. Well, strictly speaking, in any case, a frictional force is acting on that box here due to the normal, right? But of course, the frictional force is a different one. It's at rest compared to when it's moving. So typical, the frictional force when something is at rest is higher, and we usually bring that into relationship that we say that frictional force is a factor mu times n. So that frictional coefficient, that's either 0 or 1 to indicate it's either the one at rest or the one in moving. And typical, the gradient 0 is higher because it clearly, you can test it out, right? It needs much more to start moving a resting object compared to one which is already moving. And that's why, because the frictional coefficient is different, which means that this force gets kind of translated into a horizontal force with a certain factor, less than 1. Or if it's very, very sticky, can be close to 1, like 0.99. So that resulting normal is giving a frictional force which is maybe nearly close to the normal. And when it starts moving, the frictional force is less. And you can see that here, right? So we have 98.1 Newton down. So that means the normal is actually 98 Newtons as well. But the frictional force is only 12. So the factor is roughly like 1/8. Huh? So like 0.12, something like that. That's a very low friction coefficient, actually. But it's typical for something which is moving. If it would be static, it would be at least 0.8, 0.7, something like that. So is that concept clear to you, Chris?
Yeah.
So that basically you can say the transformation of the normal into a friction. This is, of course, you may want and say how can that happen? That's something which is going into the certainly becoming a horizontal. Yeah, good question. But for the time being, we leave that aside and just say that the relationship is that we say the weight force is equal to the normal, and the normal results in a friction force, which this friction force is a fraction of that normal. And that's defined through that friction coefficient. So having said that now is, okay, so strictly speaking, without having completed the picture yet, the box would clearly move in that direction, right? Because that's the friction force. So which force is missing?
The tension.
Okay. And the tension is how much?
It's also 39.24 Newton.
Exactly, huh? All right, okay. So because this is this one, right? So that's T and that's T. And that's therefore equal to 39.24. Very good. Okay, so far so good. So now, what is the acceleration of the box, right? So what is the next step?
Minus the 12.
Yes, right. So we have a delta F, also a differential. We have a force difference. And of course, one is 12. Now it depends on which direction we are looking at. But let's say, for the sake of the discussion, we make this one the plus direction. So we make 39.24 minus 12. That's 2724, basically 28, but that's okay. All right, so now we have the differential, right? So that means there's an additional force pulling, obviously, in that direction. So that's the resultant, as always, the net force, so to speak. And how can we get now to the acceleration? What is the... Yeah, please go ahead, sorry.
When I think of it, it's only the 10 kg one. But I think that because the 4 kg box is not on the surface, so it doesn't get affected by the friction. So the 4 kg is just like the weight that pulls on the 10 kg.
Okay, I understand what you say. It's actually not correct. That's why the answer is a different one, and I explain to you why. So the first thing is what you clearly say is it's mass times acceleration, right? So the very core actually of Newton, that we say any force is related to an acceleration, which is or force is proportional to acceleration, or when you include the mass, then it's equal to mass times acceleration. And clearly, the question is now, so in order to get the acceleration, we take the delta F divided by m. And now the question is which m? No? And that's why I was asking if it has been dealt with in class. It's a very special situation. And of course, the same thing applies for the elevator, actually, because the system, without going into the details of the theory, is as such that you have two masses involved. And you can derivate when you start to look into details, which I don't do today, actually, but because it's taking too much time. But the bottom line is that we have to include both masses, because the system, so to speak, consists of both masses, and they are both part of that acceleration or the resulting force, actually. So it's not just the 10, it's that one as well. And that's irrespective of the friction. Basically, like you say, this has to do with the tension. So yes, the direction here is in this, but the pulley makes it as such that it goes that way. So in other ways, you can actually as well say it's like that.
Oh.
Because clearly it's like transformation of the force into a different direction. That's what the pulley does actually. It's like a vector change, so to speak. It changes it from y to x and assuming frictionless, right? So that's why that one goes into this one, or the other way around then, of course, one on one. And because of that, of course, both masses are involved in that situation. And it's when you really think about it, again, as I say, we could really explain it in more detail, but we don't. But nevertheless, you can say, well, of course, basically there are two masses involved, right? Which are going into, and they're both going in that direction. That mass goes in that direction, and actually this mass, when you extend that, is going in that direction as well. Just because of the pulley, it goes down, but that's irrespective. And that's why something similar happens here as well. Although here it's a bit more obvious because you can see, well, they are both in the vertical, right? So that one is a bit more obvious that the pulley here acts so that both masses will be part of it. Whereas here, it's a bit less obvious, but the effect is exactly the same because of that one translating it. So that's why this one is then in the end, so our 27.24 divided by 10 plus, also in other words, by m tot included. And that's why it results in 1.9 meter per second, huh? Which is this one.
Okay.
Okay.
Yeah.
Yeah, I mean, it's a bit, just, well, it's one of those, again, where you can accept it, so to speak, that the pulley acts as a directional change of the force. And hence, when you consider that, you can clearly see, well, of course, there are two masses involved in that one, not just this one, right? Yes, we think this is pulled down. This one is pulled down here, but that movement here only happens because this one is pulling. But yes, it pulls it down here, but because of without the pull, strictly speaking, it could as well pull in this direction, right? But then, of course, where would the gravity come into play? So that's why it's a very elegant solution. Actually, somebody found that out many years ago, that this is actually like a change of direction for the forces. So you can have the same force in this situation of the pulley, but you can utilize the force of the gravity in order to pull something forward. Very practical, actually, right? So you have to make sure that you have a pretty smooth surface with as little friction as possible. You must have something to hold the weight in place here, for example, maybe a lever, which then is dropped or slowly released. And then this one starts to go down, depends on the height. Of course, it will generate more forces the further down it falls. And hence, that one gets pulled in this direction. So instead of pushing it, you have an external force doing the job for you. But why is that moving in that direction? Because this one is falling down, which means in effect it's actually the force acting in this direction. That's exactly what we said here. But if it's like that, then of course that mass is involved as well. We cannot then just say, yes, this one is being pulled, this has the force, but this one has to be pulled down as well. So it's part of the system. And hence the 14. Huh? So when we look at the next one, can you just guide me through? Maybe you see, I mean, this is actually the principle you see. There's just something again. What is missing now when you look at your calculation and you come and think about what we just discussed right now in terms of the involved masses? What is probably different now here in that calculation to get the acceleration? Sorry. So which mass did you include here? I think 1280, I think, right? If I read that correctly.
Or yeah.
So that would be the passenger car. And I know it's tempting. Here it's a bit more obvious than in the other example, actually, with the result of the POI, right? If you have, what happens is you do not have just that one with 1280. You actually have this one as well with the 1320, the balancing weight, which is actually more, right? I mean, it's a bit tricky here the way the way they show it. This one is obviously more than this one, but it's drawn smaller. I mean, of course, it's not the proportion. You can have a very heavy lead weight pulling it down, of course, so it may be really less volume. But of course, from a impression point of view, this is a bigger force. So Hainsworth, this is eventually a bigger weight. But nevertheless, it's like it is. But you just have to keep in mind this is more, right? So slightly more. And Hainsworth also has the mass, which results in the respective forces. And it's the same story. Obviously, we have a differential. This time, one pulls obviously more than the other. Both are under gravity, different to the other example, right? So this one is then whatever weight times 12. Sorry, like you did it actually. The 128 times 9.81, and you have this one as the 1320 times 9.81. And of course, as a result, you have again that differential force, right? And the differential force is clearly on this side. We can see that already from the masses. That is in the magnitude of 392. Huh? So that's the net weight pulling down, actually, this one. So that means this one goes up. Movement-wise, let's get another color. So let's say movement-wise, this goes down and this goes up. Huh? Or the other way around? Which one is it, Chris?
The other way.
The other way around, huh? Exactly. So that one goes down because it's heavier, and that one goes up. Huh? Okay, so, and again, so now we have the movement as a result of the differentialing forces. And of course, now the same story, that we say this is red. Let's go back to red. And that is, of course, mass times acceleration. And we want to know the acceleration, same story as before, divided by m. And again, here it's a bit more obvious. Which masses do I have to involve? When you really think of it. Is there only one mass involved? Or both?
Both.
Both, exactly, right? It's very tempting. That's why I was asking if you have dealt with that in class, because it's a bit a special situation. Usually we of course, then say, oh, okay, this is this one, right? Or this one, depending. But actually, we look at the whole system, and the whole system involves two masses. And the masses are are not vectors. They're just scalar, right? Doesn't matter, they are around. Even if one moves up and the other one moves down, that is resulting in the net forces, as we know, as a result of the masses and obviously an acceleration in that regards. But it needs both masses, and you cannot just say this is the one involved, because the whole system, which I'm looking at, otherwise I can't solve the problem, is actually involving a second mass. Only because of that, I do have that 392. Unless, of course, I would say, no, I'm only interested in this by some unknown force from the outside, be that electro engine or whatsoever, could be as well, right? That you don't have a weight here, not the gravitational force, but an electromotor with a spindle, which is then taking up the rope and then releasing it backwards. So first it takes it in and then releases it. Then you could say, okay, I don't care because this is only this one. And then, of course, it would only be the mass of this one, which you would have to consider it. As we would cut off the system. So physics is very often a matter of where do we lay the boundary of the system we are looking at, which is related to the question we are asking. But here we clearly look at that system. So it involves both masses. That's basically the bottom line. Same here. We have two masses. Here it's a bit less obvious because we think this is moving like that, this is moving like this. So we are tempted to exclude the second mass because it's going into a different direction. But a mass has no direction, right? A mass is a mass, and clearly both are involved here. Here it's a bit more obvious. They are both moving in the y direction. So it's a bit more obvious that both have to be involved. Huh? And that's why this one is then the 1320. And the 1280. You know? And if you calculate that, Chris, what do you get for the acceleration?
.15 meters per second squared.
Okay, yep. So Hainsworth, I make it green. Hainsworth, we get that one. Huh? Basically half, right? Because the weights, the masses are so close, it doesn't show in such a difference here actually for the acceleration. I mean, the magnitude. So it's basic because it's now doubling more or less 1320, 1280. It's very close. So the difference of 40 kilogram for the total mass is nearly irrelevant. Hence, it does basically half it, right? Compared to when you just took the 1280 before. Is that clear, Chris, now?
Yeah.
So at the moment you see such a pulley system, always include both masses. They are, and it doesn't matter if it's like this or like that. Of course, they're much more complicated pulley systems, but then the focus is then less on what we just discussed. Then it's more about additional pulleys where the forces are basically being multiplied, if you want to say so. That's something totally different. This is more like just a bit of complication to some degree of the standard balanced forces considerations. Okay. Now this one, the third one of the question form, I mean, when you go through it, so I think from what I think it's more or less a rounding. It's not a big problem. The basics are all clear the way you made it, right? You have 17.64. That's correct, right? You take that one and 1.8 in order to get the force. And then you take it into the direction of the surface. So you have to take the sine, which is correct as well. The only point is just maybe recall what is the sine of 30?
The force down the slope.
Also, when you take just the sine, what is when you take the sine of 30 degrees? What is the fraction what you get?
Wait.
No problem.
1/2.
Yes, also 0.5, huh? Exactly. Okay, so you get half. I mean, this is 0.5, huh? So 0.5 times 17, or half of 17.64 is how much?
Okay. 8.82.
8.82, huh? Okay. So actually that will have this time, this has a big impact on the final result. So how do you continue? And so we have the force, and we have to calculate the acceleration again, huh? So what do we do?
Minus 3 Newton.
Okay.
5.82.
Okay. Yep. So 5.82. So the delta F again, right? Always the delta F. So one is going the friction force is also F. Yeah, maybe I shouldn't say delta F in that context. It's a bit misleading because it says parallel to the plane. So we can say maybe because this is a bit, the F is a bit, but if I say delta F now, that's what the only thing I was thinking. But let's say it's, of course, in any case, it's F minus the 3 Newton, right, or the friction force, which is going obviously in that direction, huh? Which is 3.0. That is 8.82, huh? Exactly. And in consequence, well, let's still call it delta F, doesn't matter. And that is, like you said, 5.82. And then comes the same, so delta F, of course, is equal mass times acceleration, and so acceleration is delta F over mass. And here, this time, of course, there's no pulley involved, so that 5.82 divided by 1.8, there you see that has quite some impact, unfortunately. So if you calculate it, what do you get, Chris?
3.2.
3.2, huh? Okay, so here we go, huh? 3.2. And if you, that's why when you take the 5.73, divided by, oops, 5.73 divided by 5.73 divided by 1.8.
Wait,
So there you got something wrong, right? I mean, that's why that's 4.85.
maybe I used 8.73.
I have a feeling, yeah. Yep. Well, if you do that, right? So if you take 8.73, yeah, exactly. 73 divided by 1.8, you get 4.85, exactly. So you see the difference is not so big, but it's, I don't, obviously you didn't get 0.5 here, right? Or unless you calculated that in your head and made a mistake, right?
Yeah.
So you got the 873 actually. Other than that, I mean, again, that difference is not so big. So clearly you subtly mistyped. So even if you would have used the 5.73 instead of the 5.82, I mean, of course, that difference of 0.1 can't make the difference in that regards because it jumps really from 3.2 to 3.9. So maybe it's 3.15 or 3.25, right? Either way. So this is a good example of just recheck the numbers, huh? Because you got it clearly. You have the clear understanding about the balancing of the forces. Oops, that was the wrong one. So this one. So to talk about the delta F, which of course is always a matter of aligning them, even when you have the pulley, then it will just transform basically that force into this force. So you still have to balance it, which you did there. Then you get a number, of course, based upon that calculation. So just make sure that you punch in the numbers properly. And then, of course, you get this one, right? So, and that was clearly, basically it's okay, just why you got 5.73 instead of 5.82. It's a bit of a mystery, but that doesn't really matter. Clearly you then punched in 8.73, instead of the 5.73. Okay? So no biggie, just this is a missed point, if you want to say so, right? These two are, I would say, is a basic understanding issue, which was not clear before the test, from what I see. Now it has been clarified, so that will be no more problems for such kind of questions to mark safety in the future. This one was just a mark for punching in the wrong number. Huh?
Yeah.
But the understanding is completely there. That's good. So what about the last question? It's a tricky question, I agree. So when you go through one by one, if you take answer A, right, crystal clear, absolutely. This is what we know. This is that counter force. So this is correct, right? Correct. Well, let's go to D. D, a body continues in a state of rest or of uniform motion in a straight line unless acted upon by some classical Newton. So clearly correct. So they are the ones which typically we start from this one as the first one, then the next one we get to know. Now comes the momentum, because these are the third laws of Newton, which we just apply them new, so we don't really take the text of his book or tractate from that time. But if you compare them, which one of the two must be wrong, right? Because these two are right, so we have to make it a bit by exclusion. When you look at B, does that make sense? The rate of change of momentum is directly proportional to the external force acting on the body and takes place. Sounds very logical, right?
Yeah.
Right. So let's put that into brackets. That seems to be very logical. What about the next one? Anything which bothers you when you read it? I mean, the total momentum of interacting bodies remains constant, providing no external force acts. It seems to be a pretty strange statement, frankly speaking, right?
Mm.
It sounds somehow okay, but yet, on the other hand, why should that total momentum remain constant? If it would say before and after, right? Something happens. For example, like we saw in these examples, one body hits the other body. This one is at rest. This one has a velocity. Afterwards, both bodies have a velocity. Right? So clearly then we can say, okay, the change of momentum, say two bodies collide, then the momentum, the momentum, the total momentum will not change. That could be something like what it says here, right?
Yeah.
And external force, well, if that one is moving, of course, with the mass involved, but we don't call that a force, right? We call that a momentum because it's m times v, not m times a. And they are not talking about the change of momentum. That would be something else again. If you talk about the change of momentum, they just say the total momentum remains constant. So it's a bit a strange sentence, frankly speaking. So we only have the choice between B and C. B seems to be very logic because it talks about the change of momentum. It's proportional to the external force and takes place in the direction of the force. That seems to be very logic. It makes sense. Whereas this one is a bit strange. So that's the only explanation I can give for the test, right? That you have to go through it and say what is very clearly correct. Okay, correct. Then the remaining two, which one of them is less likely correct? And
maybe it's because it's not like one of the laws.
exactly, right? It's not exact. That makes it a bit difficult, right? I agree. Well, A and D are clearly basically the text from Newton's book, more or less, right? Or at least properly transcribed into a modern language. Yep. So that's a bit. These type of questions they arise. So sometimes at the moment or in the moment of the test, yeah. Then you say, wait a minute, I can't really recall that I've read it like that. So applying some logic then is the only way, and then thinking which one is more likely correct than the other, or which one is less likely correct, right? That's along the lines of what you can think, huh? Okay, so sorry, and we go this way, huh? All right.
Yeah.
Then I would like to do some more questions today. Some of them are more related to moments, because I found a couple of questions which are a bit less obvious. That some of the moment questions are really simple, but I think it's good to deal with some of the more complicated ones. And 7 is a good one. This one looks very complicated, right? And it's a multiple choice, but multiple choice doesn't mean you have to do some calculations, right? It's only that an answer is given, but you basically can disregard it at the first moment and say, well, whatever, because you have to go through the motion of the solution in order to come up with your own number and then compare it. Which one of the A, B, C, D's is it actually? So moment, huh? So the force, and because this one is less obvious, a bit of a moment question at first glance, because it's about balancing forces. But of course, as the forces are applied in a certain distance to a center, we have to consider, obviously, then the moment involved and go backwards, so to speak, because a moment is force times distance. So we are asked for the force. So this is an interesting question. And when you look at it, we have force applied this way, force applied that way. What is the resulting turning of the spindle of this one? So in which direction will that turn?
It should be. Oh, it should be turning clockwise.
Yeah, very good. Yeah, that's already very helpful. So moment questions always have a lot to do with in which direction, right? So it will turn clockwise. So that means, what does that mean for the moment, for the clockwise moment now? How? Excuse me. What is the total moment? in clockwise direction, because in moment we usually think, instead of x and y, we think rather clockwise, anti-clockwise, right?
It's just 1.6 f.
And why is it like that?
Because there's 2f, and
It's really...
the center, the point is 0.8 from the
okay.
f, so
2
times 0.8 is 1.8.
Exactly. Yeah, very good. Exactly. So either plus. I will write it down as a plus because they're adding up, but of course you can write twice. Exactly. Yeah, very good. Okay, so we have a total moment clockwise of 1.6, right? Now, what is the anti-clockwise moment? Sorry.
0.25 times 800.
Okay. Right, because you take clearly that's the distance here, yep. In that direction, and we have the 800 because of the weight, huh? Exactly. So that's the interesting part, right? So that's where we have to say the distance here from here to here from the pulley is absolutely irrelevant. That's the important thing, right? So the pulley in this case is again simply helping us to transform that downward force into moment force here, right? In this case, or depends on where it is, doesn't matter. So in order to pull that around, so we could as well have some external force just pulling it in that direction. That would be the same effect, right? A person stands here and pulls it straight ahead. That would be the effect of a person pulling it straight like that. The beauty of the pulley, same thing like we had before, it just transforms the direction of the force. So in this case, the one going down is becoming a force pulling over here. So we use gravity, so to speak, in order to exercise a force in the direction we wish it to be. So that's like, it's like a transformation of the force direction thanks to the pulley. Huh? Okay, and what do I have to now? So that's one. So that's obviously 200. Newton. Huh? So, and how do I solve now the final question?
Just 1.6 f equals 200.
Yeah, exactly. Huh? So when we say the minimum force, then we can say, okay, when they are equal, that's in that case, the minimum force. That's just when it starts. I mean, of course, they are right now at that moment basically balanced, but a tiny weeny bit above it, it will start to move. And that's exactly what we take into place, into our consideration. Huh? Exactly. So Ainsworth F is how much?
125.
125, exactly. Huh? All right, so that's the solution. And hence B is the answer. Huh? Okay, so that was, again, using the pulley, having the balance of forces, but as a result of moments this time, at least from one part, this one, and this one as well is acting in a moment as well. And henceforth, we can figure out the necessary minimum force we have to apply here. So if we would have another pulley, Chris, so in order to say that force is being generated, if you look at it from above, say this is the stick, so to speak, and this is the force. So if we would have a pulley here, then pulling down, which mass would that be? In very simple terms, what would be the mass of the body if you would have a spindle in order to generate the force, so that you get F? What would be the mass? You know what I mean?
Not really.
Okay, so like now we say, okay, you have to apply the force, right? So how do we apply that force? Clearly, that could be a person pushing, right? And applying that 125 Newton. But if you apply the logic of the pulley with the mass, using the gravitational or acceleration in order to generate that force, then you could say, well, you could have something like this one, here, here. You have the pulley here, right? So here I could do something similar and say, well, I have a rope, and there's a pulley, and there's a weight.
Oh, yeah.
So, and of course, same thing in the other direction, going down here. Huh? So what would be the mass?
125 divided by
Yup.
9.81.
Yup, exactly. It's very simple, obviously. So roughly about 13 kilograms probably mass in order to get that. Huh? And you see, that's the beauty of it. So instead of you, so to speak, standing there and pushing, and somebody else as well on the other side, then two persons pushing the lever, you could as well install a pulley, have 13 kilograms of weight, and then let it go, and it starts for whatever, so to speak. So that's why the pulleys are such a well-liked topic here and here and here, in order to generate the force from the gravitational acceleration, instead of using manpower, so to speak, or ox power in the olden days. Okay, good. Now this has to do a bit with the again moment, but about balancing forces. And you see the question. I just let you read it, huh?
Because since the books are closer to student.
Mm-hmm.
So if it's closer, then it. Wait.
Sorry. I would. It's a good point. I would start one step before, and it's always good because we talk about equilibrium, right? I mean, that is always a helpful start to think of equilibrium of forces, of moments. So the moment something is at rest, it's at equilibrium, right? Like we learned, it's either moving or it's at a constant. When you look at the two students here, and is the table moving up and down? Also, like tilting?
No, it has no moment. There's no
Yeah, exactly.
resultant moment.
Yeah, that's excellent. Exactly. So the delta moment is zero, right? Because they are in equilibrium, exactly. Or in other words, they clockwise and anti-clockwise must be balanced, right? That's another way to say it, right? Clockwise must be anti-clockwise. Because the delta P is zero. Sorry, not the delta m, we use m usually. The m is 0. So there's no. So as this is 0, what does that, and when you look at it, so of course you could make some more assumptions, but obviously we focus on the books. What does that mean for situation A on the left-hand side? You basically, because that's what you started to say, right? That's what I would say now is this the second step. So this one, as you said, is more, right?
Yeah.
The weight is more, right? So the weight force is larger. Yet it is still in equilibrium with these two. The table is not tilting. So, not tilting. Why is that so? When you look at how do you calculate the equilibrium, then you can actually more answer it. How do you calculate the moment, Chris?
So distance from student A to the books times the mass of the books. Wait, no, the weight. No.
That's coming close.
the percentage of the weight.
Okay. Yeah, you don't have to go so far. I know what you mean. You can say the weight or the force at A. You can just call it force A, which is obviously the result of student A plus books. And then we have the force B, which is just student B. Of course, the assumption is that basically they exercise the same force, right? Otherwise, it gets we can't say much more. So if we say this is a bodybuilder and the other one can hardly weight a spoon, of course, that would be ridiculous. So they are very similar. So the difference comes basically from the books. So, and as we talk about moment, so when we talk about, like you said, moment is mass, sorry, force. Force times distance, and they are clearly in equilibrium, right? So situation A is equal to situation B. But we know that force A is larger than force B because of the books, right? So FA, FB, so this is greater than FB. So if FA, I make it in red, is greater than FB, what has to happen in order that they're still in equilibrium?
The distance.
Yeah, exactly right. So we can introduce that one and say, and how is the relationship of the distances therefore? Which one is larger than the other?
B is larger than A.
Exactly. Yeah, good. Right. So that's the answer in the end. That just go straight from what we know. We know exactly how moments are being calculated, force times distance. And as clearly the table is not wobbling up and down while they transport it, at least not in this situation, in this assumed situation. It means it's taking so clockwise is anti-clockwise, right? So they are the same. Hence, we must go back to the origin and say, well, this is how I calculate it, but they are the same as a result. So who's contributing how? Or what is contributing how? Then we see, okay, the books, assuming the students are the same. So we have a higher force on this side because of the books. But the product must be identical. So the only, mathematically speaking, of course, is then the solution that this one is more, has a larger distance than A. So the center of gravity, so to speak, will change. So the turning point is not exactly in the middle, but it will obviously shift henceforth. Okay.
Yeah.
I'm just briefly checking Yeah, when you basically when you write something like that, what I just jotted down, this is going in the right direction, huh? Okay, so then the next one is now quite an intensive one, and I think it's good to go. It has a couple of various aspects we have to consider in order to come to the right answer. And it's going from A, B, C, D, E. So it has a couple of sub questions, huh? And first we get all the information. So it's a stability. Obviously, stability has to do with moment, huh? And when we start with question A1, and we are obviously starting to, I mean, it's of course completely not in proportion. I mean, that angle, like nearly 45 degrees, the bus would have fallen over many times over again. So the angle is, of course, maybe like 2 degrees, 5 degrees, 7 degrees, something like that, most likely. So the drawing, as usual, is not in proportion. Nevertheless, so it's lifted. And why would the bus topple to the left?
Is there a resultant moment anti-clockwise?
Mm-hmm. Yes, exactly. Yeah, very good. Exactly. Seems a very complicated description. At the end of the day, somehow that one is greater than this one. So the net of the moments. And how come? I mean, I already indicated it, but how come that moment is greater on the anti-clockwise side than the clockwise side? Because we see the center of gravity must fall outside the bus, right? So that's one. That's a second explanation we could use here, but one is good enough. Huh? So anti-clockwise moment. Greater than clockwise moment. Okay. And what is the effect of adding weight to the underside of the bus?
The concentration of the mass would be concentration of the mass would be shifted more to the left, so the center of gravity would also shift more to the left.
Yes and no. But when you think of it, you have it put down on here. So basically, that's the body of the bus, right? And now you add additional weights here. So what if with before the weight, you can maybe the center of gravity. Let's take the bus like it is here, right? If you add now more mass here, what will be the shift of the center of gravity?
Oh, it would be lower.
Lower, exactly. That's the key point, right? And that is exactly adding stability, right? Because it will make an impact on the turning point. Is instead of up here, it will maybe down here. So, in other words, if you look at the distances, of course, if the force attacks here, so to speak, then of course the bus will topple very easily, meaning the center. So the distance for the center of gravity, right? But if I lower it, it becomes more difficult. So the concentration of mass shifted, and that one is a good comment, and then hence the center of gravity is lower. And because it's a 3 marks question, so we have to think of subsequent results. Otherwise, I mean, there's not more to say. That is the core point, that the center of gravity has been shifted. What is the effect of that? When we think of, yeah, please go on.
Stability.
Say again once more, please. Sorry.
Stability.
Yeah, increased stability. Exactly. And that increased stability is how is that related to, let's say, when you think of the angle?
It won't topple.
Yeah, or you can say it will topple later, right? I mean, in other words, you can increase the angle a bit further before it topples. Oh. If theta 1 is the one it toppled before the adding of the mass, then clearly theta 2 will be a greater angle with the added mass before it topples, right? So what I want to say is, so basically, theta 2 can be greater than theta 1, right? So in other words, if it was before the adding was like that, then now the angle can be like this, huh? A higher angle, very practical, straightforward, but it's important that we voice it out. Increased stability, and that means higher angle or higher degree, higher angle, higher degree. Until the bus topples, huh? Exactly. So that is basically like the 3-mark question result, huh? Okay. Now, in question B. Okay, here it says you can tilt it to an angle of 40 degrees. Okay, that's quite something before it starts to tip. And now, how to calculate the center of mass when it's empty and normally parked. So, right, is when we look at back, I will erase that. And say how would we determine that?
We use the width.
Okay. Make that green. Okay, so the width of the bus is basically like here. Like here, yeah. Then where on which line will the center of mass move? When you think of the width. Will it be here or will it be here, or where is the line? I mean, at some point, yeah. Because you have a 2-dimensional problem, right? One is the height, obviously, we have to figure out the height. Like in the question, like determine the height above the ground of the center of mass. So the height, right? Okay, somewhere here. But that's the one dimension, the height. But what is the other dimension? And that is always the same, basically. I mean, assuming you have a equal density, which of course is not for our calculation realistic. In reality, of course, the bus doesn't have an equal density, but for our calculation, it's good enough. So if the density is the same all across the bus, so where do I have then to draw the line in order to determine the height of the center of gravity? You think?
Perpendicular to the width.
Yeah, exactly. And that's good. And in which direction, or in, okay, perpendicular is one thing, and in which distance? Where do I have, is it here, or where would I have to draw that?
Right above the, where the angle is, the point of the angle.
So, oops. Like this? Like perpendicular?
Yeah. And then
okay. And in which yeah.
So the center of gravity would be right above the point of the angle.
Okay, like that.
Huh? Yeah, this is the line of the.
Yeah, exactly. That's the one I wanted to drive. So that one you can take exactly in the half, right?
Yeah.
So like this, right? That's important. So the center of gravity in a uniform density, you can of course take it, or in other words, if that's the body, then you can always take it like it will be here, right? Yeah, that's not necessarily. So basically, it will attack somewhere here. Will be the center of gravity, and of course, under normal circumstances, that's where the center of gravity is, right? Center. But with the tilting, of course, it will start to shift. That's the point. Huh? Exactly. So it will be half, yeah. So that means we have, first of all, we have a 90-degree angle here. And of course, it's a bit misleading now. So that's a 1.22 because the whole width here is 2.44. Huh? Okay. All right. So now I have, now if I draw it again, I have something like this. So how does the angle come into play now? So that's my 40 degrees now. Huh? Where will the center of gravity be, Chris? Right geometrically.
Like perpendicularly, like the line perpendicularly against the floor.
Yeah, very good. Exactly. Huh? Something like that. Exactly. So there's another degree, 90 degree. Exactly. So this is my center of gravity. Huh? Exactly. And how can I calculate now the height? Because when we said the height above the ground of the center of mass, right?
Yeah.
So how can I calculate that?
I think first we put the 40 degrees at the point of the center of gravity.
Can? Oh, okay, sure. When you think this, I know what you will do, and that's okay. That's correct. What you could do as well is take the counter angle, and what would you, because that would make your life easy as well. You would straight get the reply. Because here you get a 90-degree angle, right? Yeah. So if that is 40, so how much is the one in here?
The 50.
50, right? Okay. And henceforth, in order to get the height,
it's cosine 50 degrees times the 2.44. Wait, no. The
Nope.
1.12.
Yeah, 1.2. Okay. And what else? What about the, okay, 1.22 times, what will you take for the 50?
Cosine.
Are you sure? Which one you want to know for the height, Chris?
The one on the side.
Okay. So when you look at the 50-degree angle, what is that?
It's between the hypotenuse and the adjacent.
So, okay, in other words, do you want to calculate this one, or this one, or this one?
Oh, wait. Can I see the question again?
Yeah.
Oh, normally parked. So, then it would be sine. Wait, no, tangent.
Tangent, exactly. Yep. So, okay, good that you said go back, right? When it's normally parked, right? Exactly. So then the height is the fat one, right? So to speak, huh? Exactly. So then we talk about height here. This is our height in green. Okay, and that would be, if you calculate it, what do you get?
$1.45.
Okay. They simplified it a bit here. Excuse me. Okay, so we take the. All right, so having made that calculation, excuse me, so we can quickly. All right, okay, that's 1.45 meters. Huh? All right, then empty and normally parked. Huh? So now we go a step further. And start to calculate the new height of the center of mass. Now this is all about moments. But for ease of drawing. So we have the mass of the passengers, right? And we take 60 passengers. And we have 65 kilograms. So what is the mass of the passengers?
60 times 65.
All right. Okay. So we got 3,900 kilograms. And what is the mass of the empty bus? Just the bus alone, the bus shell. Go back here.
7,470.
Okay, yep. 7,470 kilograms. Okay, so you have the two masses, huh? And now they say the center of mass acts at a height of 3.28 meters above the ground. So they're on the top deck, huh? That's the idea.
I think you times the masses by their height, and then
okay, good. Okay.
Divide the whole thing by the total mass.
All right, let's see. Yeah, that's the starting point. So we have a center. So in this case, we always have to consider the center of gravity, right? And what is how far away from what?
The road.
So we can say, let me think, where is that? This one. So the center of gravity from the ground up when it was standing was where? Let's make this the ground. Huh? $1.45, huh? That was before. Now that was in the old center of gravity situation. Now the center of gravity is shifting upwards, right?
Yeah.
Would you say so?
Yeah.
So we can make a green one. So do we know that distance? From
it's the 3.28. Wait, no.
Nope. Yeah, that's a good point, right? So it's a bit tricky, the whole thing. I mean, it's fine because what we will end up is we will have some equations. So, and the point is we have to set up the equations actually now in order to get that. So as the center of gravity shifts up, and what is acting at the 1.5 or 1.45 meter before, which weight? Because actually, if you would put it into the horizontal, it's a bit nicer to look at. But it's not reflecting the situation, but it helps a bit more in thinking of moments, right? But which force is, which weight force is acting at what height, right? And when at the original state.
The 7,470 kilos is
exactly,
acting
huh?
on.
Yep, on this one, right? So exactly. So we have this one. So that's the one at this point, which was 7,470. Huh? Also, I make it in red just to distinguish a bit. So hence, but now it has shifted up. We don't know. So I would say give that an X and just say, well, it shifted up. I don't know. It shifted up by X. And when I have like you said before, now there's a new, and it says that the passengers had a height of 3.28, huh? So I can put it here. It doesn't matter if I do it on the left or on the right hand side. I can maybe do it here. So this is 3.28 meters. 3.28, and it will act. And it says that the center of mass can be considered to act as at a height of 3.28 meter above. So obviously they act on this. Their force is here. Huh? That's what it says, right? So I can make the. Let's make it blue. So that one is acting here, and that's the 3.9. Okay. So do we know the distance from that center of gravity? Basically, that's the center of gravity of the passengers. This is the empty bus, and this is the final one. This is the total one. So again, we don't know. So you can say from here to here, that distance, I don't know either. Do you know do you see what I'm doing, Chris?
Yeah.
Because, right, when you look at it, I say, I know that when the bus was empty, I had the center of gravity here. Here. So that was 1.45 meter as calculated. And that's the weight of the mass of the bus, acting there, then ultimately as the force with the G. On the other hand, I have the passengers. They're at a height of 3.28 meters, it says it clearly, and they have the calculated mass of 3.9. So it's up here. So I know this distance now, and I know this distance. And I know this was the previous center of gravity for the empty bus, and this is the one if there would only be the passengers without the bus and anything. This is this one. But, of course, I know there will be a resulting center of gravity for the total solution, but I don't know the distance. What I know is will have a certain distance here. Between the empty bus, it will have shifted up, guaranteed, because of that weight up high there. However, that center of gravity here will shift down because of the bus pulling down. So I have another distance. So I have introduced two unknown distances to the new unknown center of gravity. So this is what I have established by thinking over the moments situation of the two contributing forces or moments in the end. And what can I say now under the normal situation? What are these moments? Will they be in balance or not?
No.
Okay. They will be. Otherwise, the bus will topple, right? Because it says it must be safe and carrying passengers. And when it has 60 passengers, it should still be okay.
Oh.
So that's for the safety test. So it's indirectly said. That makes it a bit. So what we have to consider is that, okay, my two moments are in balance. And which two moments are in balance? Actually, the one from the bus times the distance to the center of gravity. So that's my x. And on the other hand, the one from the passengers to the center of gravity, which is my y. So because they turn around here, right? So on the other hand, if these two moments are in equilibrium, the bus will not topple because they are the same. So the one from the bus pulling it down and the one from the passengers trying to topple it over, they will offset each other if everything's okay. Do you follow that argumentation, Chris? Or I can say, let me say. So what I'm saying is the mass of the bus, also the empty bus, times. Oops, I shouldn't use this one now. That's a bit misleading. So mass of that bus. I start all over again. Times the x distance is the same as the mass of the passengers times the y distance. So in other words, this one creating which is this distance from the center of gravity has to be as the moment of this force to the center of gravity will be the same as this moment from this force to the center of gravity. So the trick is to see that. That's really not easy, you know. So that's why it's about introducing. Well, we talk about moment, so it must be mass times distance, and I have clearly two known values. I mean, distances values. I have the height of what it says for the center of gravity for the passengers, and I have the height of the gravity center of gravity for the empty bus. But I know there will be a new center of gravity as a result of that. And in order for the bus to be stable, it always comes back to the same. So you will hardly, even if it says, when will the bus start to topple over? Then you say, well, when one is bigger than the other, right? So you just start at the equilibrium and then one will become more. So as the passengers are ultimately flexible, then you can say, well, I add more passengers. So clearly this is the one, the bus will not change, right? So you will increase the mass of the passengers until it topples. But at the moment it's safe. For whatever reason, they say 60 still has to be a safe number, okay, because maybe 60 seating places upstairs, whatever. And then there must be an equilibrium. And then you introduce the concept of the unknown new center of gravity and the respective distances of the forces you know to that center. And because you have the old situation, empty bus, center of gravity, the assumed theoretical situation of center of gravity just as a result of the passengers alone. And then, of course, you can say, well, I have a distance between my assumed center of gravity, which I call y. We could just call it dy, dA, d passenger, whatever. And of course, I have the same for the empty bus. I have a distance unknown x, or the distance of the empty bus towards the new total center of gravity. And they must be equal. This is this result.
Yeah.
And when I take the value, so I get something like 7,470x. So then I can really start to simplify, kind of, and say 3,900y. So now comes math into play, because now I have one equation for the time being, but two unknowns. I don't know x, I don't know y, but right now I only have one equation. Huh? So how could I now express one of those with the other? Or in other words, I can eliminate or substitute one with the other. I could, for example, y, right? It doesn't matter. And when you look at, so how could you do that, Chris? How could you substitute y and express it differently?
3.28 minus
Okay.
x. Wait, minus and also minus 1.45.
Yes, exactly. Yeah, very good, exactly. So we get in result. Now I know why they took 1.5, makes life a bit easier. So that's 2.28. Is it 83? 183? Yeah, 2,900. What is, so this is the new distance, so y equals this one. So what is the number, Chris?
1.83 minus x.
Okay. and we have 7470x, huh? Okay, so now of course I can just start to go through the mathematical motions, right? 3900x, put it to the other side, so minus, so I plus it, so I have 7470x plus 3900x equals 3900 times 1.83. 7137. 7137. And what will be my resulting x in the end, Chris?
Uh, 11370 divided by 1.59.
Which value did you divide by what again?
Wait, let me try again.
Just look at the equation here, right? So what we did was we multiplied 3900 times x, so it's minus 39, but I put it to the other side, right? So I have all the x's on one side, which leaves me with the 39 times 1.83, which is 7137. Huh? Now, of course, I can add up the x's and just then divide the 7137 divided by whatever the 39 plus the 7470 is.
Oh.
So I'll make it like that. Running out of space.
Oh, it's 0.6228.
Okay. 628. Huh? Okay, good. All right, very good. So now we found our x. So in consequence, of course, so I can, and it doesn't matter, right? I either go from 3.28 minus y as the result in that point, or my 1.45 plus my x results in that point. So it's like one of those equations where you come from two different sides, like one hitting the other, but they have to be at the same position. So in that case, I can say my center of gravity, just here, my new center of gravity total will be my 1.45 plus my 0.268. Huh? As I started to solve it for x. And that would be 2 point, how much is that, Chris?
$2.08.
Yeah, exactly. Huh? So we have a massive shift, right, from the empty bus by from 1.45 to, well, 62 centimeters up. That's quite something. So over 2 meters actually. But on the other hand, of course, you can say as well, it has been reduced. We haven't calculated that, but from the center of gravity for the passengers alone by the amount of y down to the 2.08. So basically, you can see this is 3.28, 2.08. It's like 1.2 meters. So obviously, y we can see is about 1.2 meters, right, from that one. So that one has brought down substantially because, well, of course, the bus is nearly double the mass of the passengers. So of course, it will bring it down significantly lower from this one to the center. And hence, that one is less of an impact just by 60 centimeters, which is still a lot compared to 1.45, but still. And accordingly, will be resulting this 208. Huh? Okay, so the that was an example which I wanted to bring up a bit. Like you may end up with something which has two unknowns. So one equation of course, is not good enough. We can't solve it because we have two unknowns. But then, of course, the proper drawing will help us to identify that. We can say, well, I can express one with the other, right? So I have all the data, so I can express actually y as a function, if you want to say so, of x, right? This is what it is. So 1.83 minus x is actually y. So this distance here, and we can see that clearly. So the difference in distance here, this one, and if I take that remaining one minus x, of course I get y. So it needs a bit of a mix between the physics of realizing what are we doing in terms of moment and the shifting of the center of gravity, and hence we have the resulting moment as that result of a shift, involving the respective masses, which of course result in forces, because we talk about gravity. And then we have to solve the problem that the resulting equation is having two unknowns, so we need to sort that out. But we have, if we did the graphics properly, we can see that very fast. If we didn't do that, then it will be very difficult to solve. That's my point. And then the rest, of course, is just some algebra actually to rearrange the equation and get the numbers. All right. So next time, I would say that's it. I just want to go back a bit to the moments, and then we can continue. Do you have anything specific, Chris, you would like to do next time, where you say, because otherwise I would have some questions for momentum. Or would you?
No, just momentum, I think.
Okay, all right. We will continue with momentum a bit on the similar difficulty level, like what we just did here. Maybe first one or two multiple choice, and then some more challenging ones. Huh? Okay, then have a nice holiday, because happy mid-autumn, right?
Yeah.
And see you next Friday.
Yeah.
Okay, thanks you.
See you.
See you. Bye.